promised you when you were in accelerated physics that I would do that with you. So today's the day. It'll take maybe about 10 minutes. And then we'll do a couple problems to practice. And then we'll jump in and do a lab. Does that sound okay? Mm-hmm. Okay. So here we go. So we're talking about one-dimensional motion. This is all one-dimensional motion stuff. We defined a few days ago the idea of velocity, and we said that velocity was change in position over time, right? We can say also that acceleration is the change in velocity over time. So we said those two things. If we write this a little bit less calculus-y, just to kind of keep our brains in focus of what we're really talking about. We're really talking about a change in velocity over time, which we can write as v final minus v initial over t. Is that okay with everybody? Nothing wild and crazy there? Okay, okay. So when you're talking about the basic kinematics equations, that list of equations, those 4 equations that freak the accelerated physics kids out every time. I mean, it really does. They're like, oh my gosh, and you may have been that person, or you may have been observing those people that were freaking out. I don't know where you were at on that. But the things that you need to keep in mind, this equation works in only 2 cases. Either when there is no acceleration, or if you're talking about an average velocity. That equation we will use almost never, like the change in position over time. We know that it's true that the derivative happens, okay? But I guess I should say, I guess I should say that the equation that we're not going to use is this one, if we're talking about velocity. The calculus-y version of it does take into account that we can change, and that's okay. Okay. We like when things accelerate because it's more interesting, it's more fun, it's more exciting. Okay. But from here on out, when we talk about this, the idea is that we're going to talk about situations where we have a constant acceleration. So that means that dA dt is equal to dA dt would be 0. Okay? Do you guys know what the derivative of acceleration is called?
Jerk.
It is the jerk, right? So we're talking about situations now where jerk is 0. Okay? And they are all 0 because if the derivative of accelerate, right? You know what I'm saying? So they all are 0. So that's really, we're just done with that. So we're talking about constant acceleration situations. This is the first of the kinematics equations that we care about. Okay? What's up?
Wait, is that like a dx dg is 0?
No,
or?
dA dt.
It's an a. Oh, okay.
Yes. Is that okay?
Yeah, it just looks like an expression.
Oh, I'm sorry.
Because your arrow.
My vector hat is so low.
Yeah.
Is that better?
Yeah. Thanks.
Okay. Yep. Yep. Yeah. Please let me know if I write something and it's not legible, because that happens sometimes. All right. So we're talking about constant acceleration situations. Okay. Again, there are those 4 equations. So I'm going to call this equation number 1 just so that I can refer to it, and I'll be like, we're going to put equation 1 in. And you'll be like, okay. It's not like a magical number that everybody knows. I'm just labeling it so that I don't forget. Okay. Again, we're assuming A is constant. I'm just going to start writing down some stuff. So I'm going to say, oops. If we have a changing velocity, we can find the average velocity. How would one go about finding an average velocity if it's changing? But it's constantly changing.
Initial plus the final divided by 2.
Yeah. Initial velocity plus final, because that's how you take an average of anything. Okay. And I'm also going to write down the V average thing that I said before is equal to the displacement over time. Okay. So the game here, if you look at this stuff, is that we have 5 different variables. We have A, VF, VI, X, and T. I want to establish equations with 4 of those 5. So the first one I'm going to do is I'm going to get rid of A. So the way I'm going to go about doing that, let's see, we'll start with, I think I'm going to put these 2 equations together because they're both equaling the average velocity. Is that okay? Then there will not be any A involved. So we have V initial plus V final divided by 2 is equal to displacement divided by time. And now I am successful. I mean, that is success, right? We've got 4 variables, VI, VF, displacement, or delta X, and T. Okay? We're going to rewrite it just because usually we don't see it that way. One way we see it is delta X is equal to 1/2 VF plus VI times time. That is the second of the kinematics equations. For another one, I want to establish an equation without VF. So I'm going to take that equation that I labeled number 1, this one up here. I'm going to solve it for VF. So VF is equal to VI plus AT. Is that okay? I'm not trying to go through this super fast, but I also don't want to waste a lot of time. Okay? And then I'm going to sub that in to this equation here because, well, why not? I think that's what, yeah, I want to sub it into here. So that's going to give me a delta X is equal to 1/2 of a huge mess. Are you ready for the huge mess? Here it comes. VI plus AT plus VI times T. Huge messes are often clean-upable. What can I do to clean that up a little bit?
Put the VI's together.
So if I have a VI plus a VI, that gives me how many VIs?
2.
2 VIs. And then I've got that 1/2 hanging out there. So I'm going to distribute that 1/2 also so I can get rid of that. So this is going to be something like, so that's again 2 VI divided by 2 is just going to be VI, times T, because I'm distributing from the T over there, plus 1/2 AT squared. Oh. That's the big one, everybody's best friend, right? Oh, don't grumble about that, Jonathan.
No, I'm just remembering how
You know that it's like the most important one that we use ever, right? Like, oh my goodness.
I'm just remembering how sarcastic I was whenever I talked about it in accelerated physics.
I know, but it's so perfect.
Way too early.
It's never too early for AP Physics C.
It's a beautiful thing. All right. And then, so I've got an equation. This equation has no displacement in it. This equation has no acceleration in it. This equation has no final velocity. I want one without any time in it. Okay? I'm going to take equation 1 again, but I'm going to solve it for t. So that's t is equal to VF minus VI over A. Okay? And I'm going to plug that in, let's see, where do I want to put it in? Into this one here again, except I'm going to solve it for t. I'm going to put it in for the t. So here it comes. So that's going to be delta x equals 1/2 VF plus VI times VF minus VI divided by A. And then, well, that's a huge mess too. But it's a huge mess that's kind of interesting. Because what do you notice about the things in the parentheses?
Oh, it's a yeah.
Yeah. Now, there is one little subtlety here, and it's one that I don't know that you all have addressed in math yet, having to do with multiplying vectors. Have you guys talked about multiplying vectors yet? You will do that if you're in Lane. You will do that this year.
We sort of covered it in the complex plane, but not really.
Okay. So this is what I'm going to, and we will actually talk about it this year as well when we get to magnetism, and it's really not super hard. But for now, I'm just going to let you know that when we do this, When we multiply these two vectors together, we're going to get scalars. So I'm going to leave the little hats off is essentially what is going to, the effect that it's going to have in this case. So the displacement, or the magnitude of the displacement, I should say, is equal to, so that's going to be VF squared, okay, minus VI squared over 2A. Velocity, displacement, and acceleration are all still vectors, but the values that are going to go in there are not. So that means that you have to use your brain to figure out the directions. Does that make sense? Okay. So people are always like, oh, did you forget the vector hats? I didn't. They're not there on purpose, but it's because we're multiplying vectors to get scalars. Is that okay? And now we've done it. Like that didn't even take, that took like what, 5 minutes? 8 minutes, something like that. Good for us. Yay, go team. So there are 4 equations, 1, 2, 3, 4, that will get you through all of one-dimensional kinematics. Okay. Should we try a couple problems?
Sure.
Yeah? Do you have a question? You look like you want to ask a question.
I was going to ask only, is there two-dimensional in this one?
So, yeah, so we'll do two-dimensional motion like in a couple days. But the beautiful thing about two-dimensional motion or even three-dimensional motion is that besides breaking things down like a vector that's going in 2 directions, then you just do components, and then it's just one-dimensional motion in different directions. So it's really actually quite easy. Yeah, yeah. So that's like the projectile motion stuff that we did. It's not scary. You got it. Okay. So let's see. I think. Oh, yeah. I don't know if you remember this question.
Oh.
This question is very similar to one that you did when you were in accelerated physics. It was one that we worked on. It was like 53 on a homework. It was like the hard stuff, right? So it's the first one I'm going to give you today. You're welcome. But you're much more mature students now. You can handle it. I think that if you work on it and you think carefully about it, it shouldn't be a hard problem, okay? I'm not saying it's going to take 5 seconds, but I think you can do it. So I'm going to let you give it a shot. I'm going to let you work on it together, have a conversation. Again, if you'd like to work on a whiteboard as opposed to on your paper, you can. I don't really care. I just want you to work through it. Okay? Take a look and let me know if you have questions. I'm very happy to answer them. Why don't we regroup a little bit and see where we're at, and then we can pick up anything if we need to. So A, what did you get for A? 7.96 what?
Seconds.
Seconds. Is that okay with people? Does that match? And if the answer is no, then we can fix it. That's okay. That I'm not gonna get all cranky about like, as long as it's close and as long as you've shown me your work, then we're okay. Fair? Okay. Part B, how far did the 2 cars travel?
142 meters.
Is that okay? 142, 143-ish? Something like that? I mean, close, yeah? Or
Yeah.
are you sure?
I just have decimal, like rounding and stuff.
Oh, okay, okay. And, you know, it's really interesting because, like, I was just having a conversation with somebody about this. I don't remember who it was now. But, like, oh, is the answer right? Like, really, especially in this class, it's about process. So, like, whether or not the number is right is not what I'm really interested in. It's the process that you're going through. Part C. 35.8 units. Is that okay? Sweet. All right. One-dimensional motion horizontally, we're done. Okay?
Yay.
So one-dimensional motion horizontally, that's no big deal. It accelerates because there's a motor or something happening. Then if you take one-dimensional motion vertically, there's exciting things that happen, right? Like, what?
The frog falling.
Yeah, gravity pulls that frog down, right? So there's some acceleration, and unlike the acceleration in the horizontal direction, it's going to be pretty darn constant, yes?
Yes.
Yeah, we know this, right? Like, it just keeps falling every single time. Ah! Right? So the things that you need to know. a couple pieces. We can take the acceleration due to gravity to be 9.81 meters per second squared. Generally, I'm going to use 9.8, okay? On an AP exam, you are welcome to use 10. I would encourage you to use 10 on multiple choice questions because you don't get a calculator, and you might as well just, 10 is a really nice thing to be able to multiply by, right? Okay. On the free response, you can also use 10. They accept it. That's fine. And again, it makes it go really fast. So feel free to do that, okay? If you want to do that on homework and things like that, that's totally fine with me as well. Know that it's not exactly right, but again, we're talking about process. We're not talking about specific answer. Does that make sense? Okay, so that's the first thing that I wanted to say. Another thing is that in all of this, if we're talking about we've got an initial velocity of 0, for example, and it's accelerating, and I wanted to know the final velocity here, what are we not taking into account?
Air resistance.
Air resistance, right? We'll do a lab later in a week or so where we'll talk about air resistance. We do deal with air resistance a little bit in this class, okay, because we can, okay? But know that unless it's mentioned, we assume that there is none. Does that make sense? Okay? So you don't have to like try and figure out drag coefficients and things like that with not enough information, because that would be silly. Okay? I feel like there was something else I needed to say about free fall, but I don't remember what it was. I wanted to give you a couple of conceptual questions just to make sure things were sitting okay. We'll try a couple problems and then we'll go lab it up. Sound good? All right, here we go. So, a couple conceptual questions. These will go fast. I'm going to let you just take a look at them, and then we'll discuss them. So go ahead and take a look at them individually first, and then we'll discuss them. Number 1, which of the motions is not at a constant acceleration? Miles, what'd you say?
The alley vapor.
Why?
Because it accelerates and it decelerates, starts again, has to stop multiple times. So just going on. Yeah,
It's no good. It's just no good. Okay. Fair enough. Everybody okay with that one? Number 18. This is the contentious one. What'd you say? Or maybe it's not contentious. Zach's like, why is it contentious? Jonathan wants to share something. Go ahead.
The result will be altered, and the final velocity will be lower. Well, the magnitude of the final velocity will be lesser.
Do you guys agree?
True. Yes. Solid.
No? Okay.
Good.
19?
Yes. Yeah.
Yes?
We already had
Yeah,
this
We've done this one before, haven't we?
Spinning.
But it's important. It's an important question.
For 18.
We must repeat it multiple times.
We are. You are welcome. Give me an example,
I'm
Evan.
not going to use the same example.
Okay.
Or at least not trying to. The weight on the spring going
Oh, that
Oh,
one.
what
Yeah.
Johnny We're on
It's
ice.
the most
Yeah,
abysmal.
the video game.
Actually, this time I put down.
All right.
Spinning in place.
Can an object have a zero velocity and non-zero acceleration? The answer is what, Evan? To number 19?
Yes.
And what is an example?
I didn't get that far because
Oh.
I got to yes, but I didn't get to the example.
Wait.
Oh my
19.
gosh. Go ahead, please.
20.
You're evolving the air, the acceleration is negative due to gravity, but it stops at the velocity of 0.
Right. Did you guys all hear that? Or were you talking over? That's really, come on. Throw the ball in the air, right? Acceleration due to gravity is what? Always. Like it doesn't change. The entire trip for the frog, acceleration is always down. Negative 9.81 meters per second squared. Always, always, always. Regardless of the frog's velocity. Right? Okay. Can an object have a zero acceleration and non-zero velocity at the same time?
Yeah.
Yes.
Give an example of that. You've told me something already. You've told me something already. Somebody new. Go, Matt.
If someone's just going at like constant velocity.
Pretty exciting example, yes. An ice skater is moving at a constant. Okay, there you go. That's more of that. All right. Good show. Let's do a couple of problems. That one's not very exciting. Let's see if I can find one that's more exciting. Why don't you try this one? So the game is that all of the equations are the same. It's just the acceleration due to gravity is the acceleration now. Why don't you give that one a try? Go. And then we'll do my favorite one. And then we'll do our lab. All right. So for the first part, with what speed did he throw the ball? Should we compare answers, or should we talk about how we get there? What would be the best way to do this?
I think. Do you want to compare answers?
Sure.
Okay.
What did you get?
I got 15 meters per second.
Did you get 15 meters per second? Was that a yes, that's what I got, or no, that's not what I got? Yes?
Sig fig my results.
Yeah.
Should we go through it? Okay, let's talk about it. Okay. Let's talk it through. So how does one approach this question? What are you going to do?
Well, right.
Get us started.
I assumed that it would take the same time going up and down, then I worked it backwards, so
Okay, so tell me what your givens are. Let's start there.
acceleration is 10 because I'm working
Negative?
backwards.
Right? You can use 10, but make sure it's negative. If you don't make it negative, it's not going to work. Okay? Has to be negative. It's a vector. It's going down. Okay, what else do you know?
Time would be 1.5 seconds.
Okay.
The initial velocity would be 0.
So I'm going to make a note here that this is because it's just halfway.
Looks like this is the B, the second part of it.
And then what was the next thing you said?
I just worked it backwards.
It's okay.
Initial velocity would be 0.
So we're talking about it coming down?
Yeah.
Okay. So you can say VI is 0. You could also say that if we're talking about it going up, that the final velocity is 0. Is that okay? If you're just talking about halfway, when he gets to the very top, his velocity is 0. So one of the velocities needs to be 0. And then you can solve for the other one?
Yeah.
Okay. Does that make sense? Is that a legitimate way to do this question?
Yeah.
Sure. Use something like A is equal to VF minus VI over T. Is there another way to approach the question that is equally valid?
Yeah.
Go, Miles.
Since the ball goes up and then comes right back to the same place, you can just say displacement is equal to 0.
Uh-huh.
And then use our favorite equation, delta x equals vi times t, where t is 3 because it's the whole time,
Okay.
plus 1/2 at squared.
Oops. Let me put an S there. Yep.
Yeah, that's more complex.
Well, they're both fine. In both of them, you have to solve for something, right?
Yeah.
Yeah.
It shouldn't matter. Either way should work. What did you get, Miles, when you did it?
Oh, 15.
15. Is that okay?
Yeah.
Okay. Either way is fine. They're both right. They're both really doing the exact same thing, just looking at it from a different perspective. Okay. Any issues or questions about part A, or the first part of the question?
We could just call them parts A and B since we've already started doing that.
Sure, I suppose we could, couldn't we? All right, part B then. How high did it go? What height did it reach?
11 meters.
11 meters, he says, with enthusiasm.
Oh, wait a minute. Wait a minute.
Do you guys agree with that?
Yeah.
Yeah.
Might.
I do agree.
Somebody else talk me through it. What are the givens? Let's at least write our givens down.
VF is 0. Oh, wait, you have VF. VI is 0. Okay, so VI is 0.
VI equals 0.
VF.
So this is on the way up, or this is on the way down.
Yeah, I mean, just keep with how you did it.
Okay.
And we just found VF to be 15.
And so you got A is 10 negative meters per second squared. You're looking at your time. Did you use your time here?
Yeah. Well,
Is 1.5 seconds.
And then VF is 15.
Do you even need that?
Well, I mean,
No.
it makes it easier. You don't have to do
Oops,
as much
well.
stuff if you just use your VF. Because you can just do 1/2 VF times T.
Okay, now, is there an advantage to doing that? Or is there a disadvantage to doing
the
that?
disadvantage is if you got the first part wrong.
Yes.
But won't they give you error carry forward?
So they will, yes, but I will tell you that sometimes it will result in you getting an answer that makes no sense. Do you know what I mean? So if you're looking for a delta x and you have something totally wrong here, then you might get a delta x that if you step back, which you should after every problem and say, oh, does that answer actually make sense?
Well, that could actually help you though, because then you could be like, oh wait, that means I was wrong in the first one, so I'm gonna fix that.
Or you can just.
Bam.
Or you're just not, then you get frustrated and you have no idea where you screwed up.
Yeah.
Right?
Yeah.
So, I mean, there are goods and bads. Like, if you had an infinite amount of time, then you could do it both ways and then make sure that it worked both ways, right? I mean, like that, but yeah. My recommendation to you would be whenever possible, don't use the answer you just found in the next part of the problem.
Unless it's blatantly you need to.
Right.
Like, yeah.
Projectile motion. Are we okay? Can I throw a hard one at you real quick? Is that okay? I mean, this one wasn't super easy, but there are a bunch of them on here. This one's my favorite one, though. So let me let you chew on that one for a little bit, and then we'll go drop stuff.